Hello and welcome to this simulation. Today I'm going to do a model of low velocity impact over the reinforced concrete slab strengthening with the FRP strips. This is a paper, you can see that this paper did something like our purpose. You can see this is a rebar or beams. This is some model of the CFRP form. You can see that, and this is already another form. And after that we have the numerical result here. This is the experimental result, and this is the numerical. You can see that it used the triangle mesh or tetrahedral mesh. I don't know why the writer used that element. This is a very bad element to calculate the stress in contact in the impact model. I don't know. So let's me to create a model, something similar with this paper. First I create the slab or concrete, everything. For instance, a slab deformable 3D solid extrusion, approximate size 3, click on continue. Create a rectangle, first point -5, -0.5, half meter, and again half meter and half meter. This is the square with 1 meter length, you can see, and press done, and the depth is 8 centimeter. This is our slab. We have another part named is beams. It is 3D deformable solid wire planar. Continue. Create again a rectangle. This length will be 90 centimeter or 0.9 meter. Again 0.9 meter. See that? Fix this point, and now create two line. This is and this is. So use this option, select this, and copy this 15. You can see it is okay. 15 centimeter distance between them. And now select this. Again, increase that 15. It is okay. And this is the beam. Press done. This is our beam. And we have the FRP. The FRP shell planar. Click on continue. Create a rectangle. It will be 1 meter. And it will be 5 centimeter. You can change that. This is arbitrary. And the hammer or rigid body, the impactor is discrete shell revolution, approximate size half is okay. Continue. Create a rectangle. The radius of rectangle is 5 centimeter, and this length will be, for instance, 20 centimeter. And use trim to remove that because this is a shell part. Press done, and the revolve degree or 360 degree. Assign a reference point to here. Okay. Go to material. In the material, first let's me to assign the mass to the hammer. Use inertia point mass. This is the point. 84 kilogram. And before the material, go to assembly. In the assembly, enter the FRP as a dependent part. Okay. Copy it along the x direction, 0.2 meter, 5, 6, it is okay. And now rotate the last. At the first point 0, the second point we want to the third direction, it will be 1, 90 degree, it is okay. And now move the middle point here to here, it is okay. And now translate it. the first point 0, the second point along y direction minus 0.10 centimeter. I think it is okay. And now again use the linear pattern, copy this along y direction 15, copy that, it is okay. So let me to merge it, create a composite part. This is composite, you use a remove intersection, and now select this, it is okay, that's good. In assembly, the design tree removes these parts, just we have one part. Okay, go back to material. I put the Excel file compression cdf'(c), you can change that. For instance, 30 megapascal, press enter and the data change and go to page 3, and now you will have the diagram. You can see it is 13. This is the compressive behavior, compressive damage. This is for static, tensile and tensile damage. And for dynamic, you can see it is, these are for dynamics. Okay, and if you want, change it. For instance, you want, for instance, 60 megapascal, press done and go to page 3. You can see it is 60. So I save this Excel file in the folder which you provided. For this is the folder and this is the file. Okay, so I okay. So let me to enter all the material data from my library. For the concrete, I use CDP data at 75 megapascal, and the CFRP, where is the CFRP? This is, no, this is not appropriate. this is CFRP and this is a steel. Let me to check it. First, the estimated density here, 7,800 kilogram per meter cube. Elasticity here, 200 gigapascals, Poisson ratio 0.3, and the plastic behavior here is isotropic. 360 megapascal is 0 and 700 megapascal is 1. We use them for the beam element. Again, CFRP, normally we use Hashing damage criterion to predict the laminar damage, composite damage after the impact, explosion or something like that. And these are the data. You can see these are the stress data in 3 directions. This is the first direction and this is the main direction. This is a normal direction on the composite surface. For instance, we assemble it in XY plane, so the zeta will be normal. So these are the main stress for the main direction, and these are the another direction. Tensile and compressive stress. The density is 1800 kilogram per meter cube, and the elasticity we can use engineering constant or lamina to define the anisotropic material like the composite, because we know that the composite has different behavior in 3 direction. Okay, and the concrete, the density 2450 kilogram per meter cube, elasticity 23.5 gigapascal, Poisson ratio 0.2, and here we use concrete diamond plasticity to model the plasticity. This is the general data, dilation angle, eccentricity, car viscosity, and the compressive behavior at 75 megapascal. You can see the data. We extracted the data from the Excel file, and you can change that and use own data. And the compressive damage, you can see that this is the compressive damage, and around 99% damage. And the tensile behavior, you can see that, and the tensile damage based on S string, you can see this data. Okay, let's me to create the section. First, the slab section, solid homogeneous continuum, material is CDP. The another is beam. Beam section is beam, continue. We need the circular profile. It is 6 millimeter for all, and the material is steel. So assign it to this part, beam, and we need to define the normal orientation. So it is the normal, and it is the tie is normal. Okay, and press done. And now the slab, assign the slab section to this part, and the last one is composite. For the composite, I want to use conventional shell, continue. Click right here, edit region, select this, and the material again, click right, CFRP, the thickness again, click right. For instance, a half millimeter is a thickness for each layer. And the dilation angle, for instance, the first layer 0, the second layer 90. We can change it 45, 45, or any other things. And I use bottom surface because it's extruded along the top direction. Let's me to check it. 10 here along the top direction. Okay, so here this is the top direction, so we need to rotate it along x direction. The first point 0, the second point 1, 180 degree. It is okay. So this is the surface. Let's me to use datum point, midway to point between this point and this point, and now translate this point to 0, 0, 0. And now into the concrete or a slab, it is okay again. Again, midway to point between this and this, between this and this. Okay, so like translate the concrete, this point to 0, 0, 0. It is okay. And now the beams. So the beam we used here, assembly, you can see that. Let's me to remove them. Okay. So translate, this is the middle point to here. Okay, and now select the instance beams, move it along y direction. The first point 0, the second point 5 centimeter along y direction. And the last one is rigid. Enter it, rotate it along x direction. The first point 0, the second point 1, 90 degree. It is okay. And let's me to move this point to 0, 0, 0. And now translate all these parts except the rigid body along the theta direction, minus 0.08 centimeter. It is okay. And I translate this along the theta direction, 2 millimeter for a clearance. It is okay. So let me to replace the composite. I create a surface tie composite. Select all surface. We use tie interaction. Use purple. Again, a slab. Replace it. So the surface name is slab. Okay. It is okay. Let me first go to mesh, and for the slab I want to create a middle point by use partition point normal. This is point, this is normal. Select all again, point normal, this is point, this is normal. Go back to assembly. So replace the slab, create a set, name is U, select this, and create a set, another set with reaction force for these areas. Okay, everything is done. Go to a step. You can use the static implicit or explicit. Here I want to use explicit because we have unconversions and it needs a long time to be complete. So I use explicit a step with time a step 0.1. It is okay. And I got 100 interval for the better animation. I will remove the Eulerian output here, and the fader, compressive damage, tensile damage, stiffness degradation, and damage criteria, and remove the volume thickness. Okay, and now history output. Let me to use history output, remove the energy, we don't need them. Just reaction force 3, and create another one, displacement 3. It is okay. Interaction. First, let me to create tie constraint. This is tie constraint between surfaces. Which surfaces? The slab is a master and tie is a slave. Press done. And now let's me to go back to assembly. Replace the beams. Create a set. Name is embedded. And select all these beams. Go to interaction again. Create the embedded region by this. And now select the embedded. Select the host. The host is concrete. Select 4/4. This is the concrete. It is okay now. So the another thing is interaction. The contact property is the tangential behavior penalty contact, the friction coefficient 0.2, and the mechanical normal behavior is hard. And now the interaction. Step 1, surface to surface. Let's me to replace just the rigid. Select this, the brown, and now replace the slab. Select the surface, these 4 surfaces. And now press done. Let me to replace the rigid body, and I assign it the rigid constraint for certain rigid body, and select this as control point. Everything is done in interaction now. And load. In the load we have a reaction force as a symmetry for the set name is reaction. In caster we have this, or for instance rigid. For the rigid body we have displacement for this point. Just u3 is okay because we have initial velocity along zeta direction. So use the initial predefined field initial mechanical velocity, and it will be for instance minus 5 centimeter. You can change it, for instance 0.8 centimeter. And the last one is mesh. The beams, so it is okay. Mesh it. We can use more elements for this line because these are the beam. If we use truss element, we should just one element for each line. Select this, it is explicit and beam. Composite 1 centimeter. I select the quad element, mesh it. It is good mesh. It is explicit shell and reduce integration, and it is okay. And for rigid 1 centimeter, mesh it. and it is explicit. And the last one is a slab, is 2 centimeter. Mesh it, use it 1 centimeter. It is the better mesh. Explicit and everything is okay now. So go to job and create a job, continue and run it. Already I did this model by bigger mesh. It needs time to be complete. I did it by bigger mesh. Let me to check the input file. If it is okay, I will kill it, and I can check the another model which I've already done it. You can change the time and increase the time, or change the velocity, decrease the velocity, or increase the velocity. If you increase the velocity more than, for instance, 1 meter per second, or 2 meter, 3 meter, 4, maybe you got the error because of the CDP material model. The CDP can resistance against the impact. It doesn't have a good performance, but on the other hand, for the static or semi-static analysis, it is a good material model. So you can see it's need time to be complete because of the mesh. We use a small mesh for concrete slab. Let's me to check it just for the first increment. I am waiting for the first increment here. So it is okay. This is the first increment, so you need to, um, for instance, 2 hours to be complete. So I kill it and I save it. I save it in the folder which you provided as a model 2. Already I did model 1. Let's me to remove that and enter the model 1. So let's me check the result. You can see this is a result and this is a big mesh. Let's me to check the concrete compressive damage, and here this is the view, and I used, for instance, ODB. You can see the beam. Let's me to check the beam. Okay, see the compressive damage happen here. Let's me to just hold the concrete. It is better to investigate all parts separately. See the compressive damage. This is the compressive damage. See that? Okay. And the tensile damage. See the tensile damage? See? It is tensile damage. See that above? So the stiffness degradation. See the stiffness degradation. And displacement. So let me to check the composite. We use the thickness ODB view, so you can see I used this option. If I don't use the option, you can see that. Okay, this is the displacement. Let's me to check the damage. This is the damage, Hashim damage criteria. You can see this is the matrix damage. Okay, and if I got the limit for them, it has a better sense. You can see, for instance, I used 25. It is a better sense for this. See that? Okay. Or the stress. So let's me to check the beam. This is the beam. Again, I use this option for beam. You can change it. The stress, displacement, or everything. So Let's me to um, select all these reaction force and create a diagram for that. Okay, until here. So you can see this is for each node, but let's me to save and sum it. And now you can see it is the pattern diagram. And for the displacement, you can see this is for the middle point displacement. Okay, everything has done and there is nothing to do. And thank you for attention.